Hello and welcome to another episode of Mastering Quantum Mechanics Through Problems. Yes! My name is Dr. Jacob Hudis. We're in Chapter 1, Mathematical Foundations of Quantum Mechanics, and the title of today's problem is Matrix Symmetry and Diagonalization.
Terrific!
Key Mathematical Insights. Let's look at the problem on the next slide.
Let's go.
And here's the problem. I hope you're as excited as I am. Given the following 3x3 symmetric matrix A, Part A, determine the eigenvalues and corresponding normalized eigenvectors of the matrix A.
Wow, just wow.
Part B, construct the orthogonal matrix O using normalized eigenvectors of A as its columns. Verify that the matrix O satisfies the orthogonality condition, that is O times O transpose equals O transpose O equals 1, and this means that O transpose is the inverse. Part C and D are on the next slide, but I should mention you can see that A is symmetric. If you draw a line down the diagonal and reflect over the diagonal, it's the same above and below the diagonal, and it's a real matrix, which means it's Hermitian, because all symmetric real matrices are also Hermitian, and we love Hermitian matrices because those are the matrices we use in quantum mechanics.
This is unreal.
And here's the rest of the question.
I'm so stoked.
Part C. Show that the matrix A sub D, defined as O transpose AO, is diagonal, and the diagonal entries correspond to the eigenvalues of A. And then finally, demonstrate that both the trace and determinant of A remain unchanged under an orthogonal transformation. Specifically, prove that A and AD have identical traces and determinants. And this orthogonal transformation is also known as a similarity transformation. You may want to pause the video and think about the problem on your own, because I'm going to go and solve it for you on the next several slides. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis. Part A says, find the eigenvalues and normalized eigenvectors of matrix A. This is the eigenvector equation. It says A onto the vector V, which is an eigenvector, equals lambda onto the vector V. That's the definition of an eigenvector, and lambda is the eigenvalue.
Can I go to the bathroom?
This can be written as the matrix A with lambdas subtracted down the diagonal. It's exactly the same thing. The vector V is x, y, z, and this has to equal to 0. In order to solve for the eigenvalues, we have to take the determinant of this matrix and set it equal to 0, because this matrix has to be singular. So 0 is equal to the determinant of A minus lambda I. What that means is we subtract lambda down the diagonals of A, and then we take the determinant of this. To take the determinant, you take this number multiplied by this, minus this, minus 0 times something, but it doesn't matter because 0 times anything is 0, plus 1 times 0 minus 4 minus lambda times 1. And that leaves to this characteristic equation. Here's the characteristic equation, and I want to solve this for lambda, so we need to do a little algebra to make it easier to solve. The first step is I'm going to factor out a negative 4 minus lambda, which is lambda minus 4, and I'll put that in front. And then that leads lambda minus 4 times negative lambda minus 1 squared plus 1. This is the characteristic equation.
I'm loving this physics
And now
lesson.
I can multiply this out, and we have lambda minus 4 times this, and then I can factor out a lambda from there. And what we're left with is lambda times lambda minus 4 times lambda minus 2 is equal to 0. And whenever you have an equation like this equal to 0, you set each one of the individual terms equal to 0. That's how you solve it. So that tells that lambda 1 is equal to 0. Lambda 2 is equal to plus 4, and lambda 3 is equal to plus 2. And these are the eigenvalues for the matrix A. Now that I have the eigenvalues, I'm going to find the eigenvectors. So to get the eigenvectors, we use this equation. It's the same equation that was on the previous slide, and you replace the eigenvalues down the diagonals with whatever they are, and then you solve the equation. For example, when lambda 1 is equal to 0, we plug 0 in for the lambdas down the diagonal. That gives us the equation this matrix times xyz is equal to 0. And so that says that x plus z is equal to 0. That's the top and the bottom row. And then also 4y is equal to 0. So we know y has to equal to 0 and x has to equal to negative z. And so the eigenvector corresponding to lambda 1 is equal to 0 is 1 over root 2, 1, 0, minus 1. Because if x is 1, z has to be minus 1, y always has to be 0, and the 1 over root 2 is the normalization condition. Now, when lambda 2 is equal to 4, I plug 4 in down the diagonals, and that gives us this matrix times xyz is equal to 0. So the top row says 3x plus z is equal to 0, and the bottom row says x minus 3z is equal to 0. The middle row says y is unconstrained. Y can be anything we want it to be. Therefore, I'm going to choose x and z both equal to 0. That works for both of these equations. And then y, I can choose anything I want it to be. I'd like this to be normalized, so I'm going to have y is equal to 1. So this is the eigenvector corresponding to lambda 2 is equal to 4. The final eigenvector, there's going to be 3 eigenvectors and 3 eigenvalues for a 3 by 3 matrix. We get by replacing lambda equal to 2. That gives us this matrix. And then the top row says x minus z is equal to 0. And 2y is equal to 0, so I know that y has to equal to 0, and x has to equal to positive z, and so the eigenvector corresponding to lambda equal to 2 is 1 over root 2 times 1, 0, 1. The 1 over root 2 is a normalization factor. Part B says, construct the orthogonal matrix O using the normalized eigenvectors of A as its columns, and verify that the matrix O satisfies the orthogonality condition O times O transpose equals O transpose O equals 1. So the matrix O has the eigenvectors lambda 1, lambda 2, and lambda 3 down the columns. And we know that these are orthogonal because the matrix A is a Hermitian matrix, but we're going to show that in this example. So the first column is going to be eigenvector 1, 1, 0, minus 1, with a 1 over root 2 factored out in front. The next column will be 0, 1, 0, 0, root 2, 0, but there's a 1 over root 2 factored out in front. Root 2 over root 2 equals 1, and this is the eigenvector corresponding to lambda 2. The final eigenvector is 1 over root 2 times 1, 0, 1, so I have 1, 0, 1, and there's a factor of 1 over root 2 out in front.
I've been holding it since
Next,
yesterday.
I want to take the transpose. So to take the transpose, each one of the columns becomes the row. So this column becomes this row, this column becomes this row, and this column becomes this row, and that is O transpose. That's the transpose of the matrix O. And now we want to show that O times O transpose is equal to the identity matrix. And if you take O times O transpose, in fact, you do get the identity matrix. Since the inverse of the matrix is unique, we conclude that O transpose equals O inverse. And so O times O transpose equals O transpose times O is equal to the identity matrix. Part C. Show that the matrix A sub D, defined as AD equals O transpose AO, is diagonal, and the diagonal entries are the eigenvalues of A. So if I take the matrix O transpose that was on the previous slide, multiplied by the matrix A, multiplied by the matrix O, you get a new matrix. We're going to call it A diagonal, and as you can see, it is diagonal. And the entries down the diagonal are 0, 4, and 2, and if you recall, those are the eigenvalues of matrix A. And for the final part of the problem, part D, we want to demonstrate that both the trace and determinant of A remain unchanged under orthogonal transformation. Specifically, prove that A and AD have identical traces and determinants. This is matrix A. This is matrix AD. We found these on the previous parts of the problem. The trace of A is the sum of the diagonal entries, 1 plus 4 plus 1, and that's equal to 6. The trace of AD is equal to 0 plus 4 plus 2, the sum of its diagonal entries, and that's also equal to 6. The determinant of A is equal to 0, and the determinant of AD, which is also the product of its eigenvalues, is equal to 0. The trace and the determinant are invariant under similarity transformations. And this is an important property that comes up often in quantum mechanics as well as in other branches of physics. The trace of a matrix, which is the sum of the diagonal elements, is invariant under similarity transformation for any square matrix. The determinant of a matrix is also invariant under similarity transformation. By the way, the trace is often associated with the sum of observable quantities, energy levels, and expectation values, for example. The determinant is related to volume scaling as well as system solvability. AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.